Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, in this module we are studying numerical methods for nonlinear system analysis. So, already we have come across several equations. So, where we require these numerical methods to solve all these equations. So, for example, we want to solve a set of nonlinear equations or a single equation also we can solve. For example, for finding the characteristic constants or solving the characteristic equation to know the frequency function. So, we have to solve a single equation, and sometimes to find the response we have to solve a set of nonlinear equations also. So, you have seen a set of nonlinear equations in case of the reduced equation we have derived in case of method of multiple scales or in other methods also. So, our objective in this module is to solve a set of equations, and then also numerically sometimes we have to solve these ordinary differential equations, delayed differential equations, and after getting the responses, particularly we know the fixed point response, periodic response, quasi periodic response and chaotic response. So, in these responses, to characterize those responses we have plotted the time response, phase portrait. Also we should know how to plot the Poincare section, FFT and Lyapunov exponents. So, particularly Lyapunov exponents are useful to characterize this chaotic response of a system. So, we will study all these three. So, solution of a set of nonlinear equations, numerical solutions for ODE and delay differential equation, Poincare section, FFT, Lyapunov exponent. So, last class we have started with other different numerical techniques. For example, we have studied regarding the numerical differentiation, numerical integration, finding the root of algebraic or transcendental equations, partly we have covered, and today also we will see how we can use this Newton-Raphson method particularly to find the solution of equations, then solving differential equation, finding eigenvalues, Poincare sections, Lyapunov exponent. So, some of them you already know how to find, for example, these eigenvalues. So, you know how to find eigenvalues of a matrix. So, other things I will tell you the different methods. Some of these methods you have to study yourself also. So, numerical differentiation. So, already we have covered this numerical differentiation, numerical integration. So, in numerical integration we have discussed regarding this trapezoidal rule, Simpson rule, Simpson 1/3 rule and 3/8 rule. Then this rectangular rule, trapezoidal rule, Simpson's and Gauss quadrature. So, this Gauss quadrature method, so you have to study of your own. So, now let us see if we have a equation, for example, this equation you can solve to find this value of beta L, where beta L is the characteristic constant which is related to the natural frequency or frequency of the system in this way. So, omega n equal to beta square L square root over E I by rho L fourth. So, for the Euler-Bernoulli beam equation, so you know, so for different boundary conditions we can find the characteristic equation. For example, in case of a simply supported beam, so we have this equation sin beta L equal to 0, or we can write this beta L equal to sin n pi and in this case we can write this beta L equal to n pi. So, this is for simply supported beam. So, as the equation is very simple for the simply supported beam, so we got the beta L value easily, but sometimes in case of the fixed beam or in case of the cantilever beam, so we may not get or will not get this type of equation. So, there we may get a equation either 1 plus cos beta L into cos hyperbolic beta L equal to 0 or 1 minus cos beta L into cos hyperbolic beta L equal to 0, and we have to solve this equation to find the root. Similarly, so if we consider for example, in case of the cantilever beam with a attached mass, so the equation can be changed and this equation also will be different. So, in that case finding beta L will be difficult. So, in all these cases, so we may have to use different numerical techniques. For example, we can use this interval halving or the method of bisection, false position or regular falsi, Newton's method, second method and Muller method. So, in case of the internal halving method for example, so these are some of the other equation what already I told. For example, when we are adding the mass of the system, so then we can have a equation similar to this. Okay. So, you can see the book by Huffman, that is numerical methods for engineers and scientists. So, this is a very good book where you can find all these methods, and let us discuss few of these methods and other methods you have to study of your own. For example, in case of internal halving, so let us, so we have a, actually we have a function f x equal to 0 we have to solve, or f x is we have a function. So, this is x and this is our f x or y equal to f x. So, this function, so let this is the function. So, in this function, so our objective is to find the root. So, this is the root at x equal to x star. So, we have the root of this equation. So, to find this root, so in case of this internal halving, so we can take 2 points on this. So, for example, let us take this is one point and this is the other point. So, we have to take 2 point or 2 value of x. So, let for this is x equal to we have taken a and this is the value of x equal to b. So, in this method, so we have to find a point C. So, C equal to a plus b by 2. So, this is the midpoint of a and b we have to find. So, let us see. So, this in this case C maybe this is the point where C equal to a plus b by 2. Now, the next point of iteration we have to take in between A and C. So, here A and B have been taken in such way that, so F A and F B, so they will of the opposite sign. That means, one should be on the positive side and one should be of the negative side. So, that if we will find this F A, we have to take A and B in such way that, so F A into F B must be less than 0. So, it should be negative. So, if one is positive and one is negative, so A has a, so B has a positive value now and A has a negative value. So, and A, so this is the value of A. So, this is F A and this value is F B. So, F A into F B. So, you have seen this is negative. So, this way we have to take 2 value of A and B of x, corresponding to which this f x has a multiplication of these 2 has a negative value. That means, it brackets this root. So, the root x star is in between A and B. So, now the C point, after getting the C point, so we have to take the next point in. So, we have to choose the next point. So, whether we have to, so now we have 2 halves, one is AC and other half is BC. So, which half we have to take? So, now we can find this FA, if FA into FC less than 0. So, we have to take this half. So, you just see if it is between A and C, then f A into f C must be less than 0, and so this point you just see this point is already in positive side. So, if it is in positive side, then f B into f C, you can easily find that f B into f C is positive. So, we have to take the side where, so C point can be determined. The next point, so now, so A point we have to keep the A point as A point, and this we can update this B point equal to C. So, next updation will be B will be equal to C. So, so to get the next point, so between A and C we have to write this. Now, we have taken this is the midpoint of these two. So, let me take that is C dash. So, C dash or C1 I can take. So, first one I have taken, let it is C0 or C. Okay. So, next one C1 I can take, actually it is between now. So, I have updated this B equal to C, updated B equal to C, or this is the first one we have taken C0. So, this is C0. So, then, so now again we have to write the same thing A plus B by 2. So, now it will be between these two. Now, you can see, so this is the C point. So, as this is the C or C1 point, so you just see A and C are in the same side. So, both are of the negative sign. So, FC and FA are negative sign. So, now we have to see, so this point is updated at the new B. So, now this point will be updated as new A. So, this will be the new A point, the C1 point. Now, C1 will be updated as A point, and the root will be between the C1 and C0, that is the new A and B. So, the next point can be obtained between these 2 points. So, this way we have to continue our iteration till convergence occur. So, how to get the convergence? So, you can find the value. So, this value, so if this functional value f, so that x star what you are getting, the next point C what you are getting. So, if f c, we have to check f c, if f c equal to 0, then we can stop, or within some epsilon limit. So, if it is within some epsilon limit, so we can take that C as the point root of this point. So, this way one can use this internal halving or method of bisection to study or find the root of the equation. So, in case of regular falsy, so the method is similar to this method. So, but here what we have to do, so this is A point, this is the B point. Now, the C point is obtained by connecting these two by a straight line using the equation g x. So, this equation is g x. So, this is the C point. So, C point is obtained this way. So, you know this g dash x will be equal to, so we can take g dash x, either we can take these sections B C or A B. So, if we are taking the section B C, then we can write, so this will be equal to, so the slope of this g dash x is nothing but the slope of this equation, and the slope of this equation can be obtained by finding f b minus f c, f b minus f c by b minus c. So, here we are taking c in such way that, so this is f x. So, this is f x and this is x. So, we are taking the c. So, actually this is our root, that is x star. So, we will find this. So, f c will be equal to 0. So, we are taking c point in such way that, so f c equal to 0. So, we can find c. So, b minus c, now you can write b minus c will be equal to, as f c equal to 0. So, this is equal to f b by g dash x. As we know this point, so g dash x can be found. So, as we know this f b and f a, so we can find g dash x easily. So, g dash x is nothing but, so we can find So, this is equal to f b minus f a by b minus a. So, already this is known. So, g dash x is known. So, b minus c as f c equal to 0. So, b minus c equal to f b by g dash x, or we can get c equal to b minus f b by g dash x. So, in this way we can find the C point. So, after getting the C point, so we got the C point, and here you can see that f c is not equal to 0. So, this is not equal to 0. So, this is the error. So, similarly the next point can be chosen, and then the equation can be. So, now f c, so we got the point. So, after getting this point, the next point can be taken, and the iteration can be continued to find the position or to find the root of this equation. So, next let us see another method, that is the Newton-Raphson method. So, Newton-Raphson method. So, here also we have to find. So, let us, our objective is to find f x equal to 0. So, this is a iterative based method. So, which is a very good method to solve these equations. So, we can approximate, actually we can approximate this f x, that the function. So, we have a function. So, this function f x can be, so this is the function y. So, this is x, this is f x. So, we can approximate this function about any point x 0. So, let this is the x 0 point. So, by using this Taylor series, so we can write down this f x equal to f x 0 plus f dash x 0 into x minus x 0 plus f double dash x 0 into x minus x 0 square by factorial 2. So, we can go on adding, and for the kth point we can write f k into x 0 into x minus x 0 to the power k by k factorial. So, this way we can expand a function f x about a point x 0 by using this Taylor series. So, if f x is linear, so we can write this f x as f x is linear. So, we can write down this f x star equal to, let x star is the root of the equation, or we can write this f x equal to f x 0 plus f dash x 0. So, if x star is the root of the equation, then it will be x star minus x 0 equal to 0. If we are writing only f x, then we can write this f x equal to f x 0 plus f dash x 0 x minus x 0. So, as the function will have a value 0 at the root. So, at x equal to x star, x equal to x star. So, we can write this f x star equal to this way. So, now as the function we are taking linear. So, the first derivative will be constant, and second derivative and higher order derivatives will be 0. So, these parts will be neglected. So, this whole part with this whole part will be 0. So, we will be having this only first two terms. So, f. So, now from this thing, so we can write this x star will be equal to x 0 minus f x 0 by f dash x 0. So, if we have a linear function, then the root straightforward we can obtain by choosing a point x 0 quickly, and x star can be obtained. X star will be equal to x 0 minus f x 0 by f dash x 0. So, if it is not linear, so in that case, so if it is nonlinear, so in that case again we can use this first two terms also, and we can approximate the solution f x nearly equal to f x 0 plus f dash x 0 x minus x 0. So, now it will be, so we have to find the next point. For example, so this is the function. So, we will take the x k point, let we choose a point here and then we draw the tangent to this curve. So, this line is the f dash x k. So, we can draw the f dash x k here and we will take the point x k plus 1 where f x k plus 1 equal to 0. So, we will take this point or next iteration point x k plus 1 equal to, or f x k plus 1 can be chosen in such way that f x k plus 1 will be equal to 0. So, now we got this is the next point. So, you just see our root is x star, but this next point starting from x k we got this x k plus 1. Now, at x k plus 1 what we can do? So, this is the functional value. So, here again we will draw a tangent. So, you just see this tangent is cutting this line here. So, this will be our next iteration point, that will be x k plus 2. So, again we can go to this point and here also again we will draw a tangent and we will get this x k plus 3. So, you can notice that this x k plus 3 is more closer to x star. So, this way we have to choose the, so we can start a point x k. So, then we can write this f x k plus 1 will be equal to f x k plus f dash x k into x k plus 1 minus x k. So, as f x k plus 1, so this is equal to 0. So, we can find what is this expression for x k plus 1. So, from this thing we can write f x k plus 1 will be equal to x k. So, you can take this thing. So, from this thing you can write x k plus 1 minus x k. So, this will be nothing but minus. So, you can write x k. So, it will be minus f x k by f dash x k. So, taking this right hand side, so we got this x k plus 1 equal to x k minus f x k by f dash s k. So, we can write this equal to x k plus some additional term delta x k. So, in this case this will be delta x k, this will be delta x k plus 1 and this will be delta x k plus 2. So, this additional term can be obtained by finding this f x k by f dash x k. So, this whole function can be written as g s k. So, this equation can be written as g x k where k equal to 0, 1, 2. So, this way it can be written. So, this Newton-Raphson method can be considered as a fixed point iteration of k x plus 1 equal to g x k, because you know this g x k g s k can be written as x minus f x by f dash x, as f x will be equal to 0 at x equal to x star. So, g x will be equal to x. So, g x equal to x. So, this is, so if we are plotting g x versus x. So, if this is our curve g x curve, and so we know, so g x will have a fixed point at, so if we will draw a 45-degree line, so that is x x. So, this point is the, so where g x equal to x, g x equal to x, that is the fixed point of g x. So, we know, so now this g x equal to x minus f x by f dash x as at the root x star. So, if this is the root x star, x equal to x star. So, x star, so if x star is the root of the equation f x, then f x star equal to 0. So, that is a fixed point of g x as g x star equal to x star. So, we can get the g x by putting this equation g x equal to x minus f x by f dash x. So, we can get the root of this equation. So, for the iteration to converge, so we can check this g x needs to be a contraction with g x star. g dash x less than 1. So, if it is g dash x is less than 1. So, then it will contract and it will converge to the root. So, we must have to check this g dash x to check the convergence of the equation. So, already we have this equation g x equal to x minus f x by f dash x. So, we can write this, we can differentiate this to find this g dash x. So, g dash x equal to differentiation of x equal to 1. So, this f x by f dash x differentiation equal to f dash x. So, f x differentiation f dash x into f dash x. So, this becomes f dash x whole square minus this, keeping this remaining same, and differentiation of this f dash x is f double dash x. So, divided by f dash x whole square. So, if we will subtract, so taking this, so we will have this f dash x whole square minus f dash x whole square minus minus plus f x by f double dash x. So, this f dash x whole square minus f dash x whole square will cancel, or we are remaining is f x into f double dash x by f dash x whole square. So, we see this g dash x is nothing but this becomes f x into f double dash x divided by f dash x whole square. So, at the root, so when we have the root, that is x equal to x star, as f x star will be equal to 0. So, this term will be 0. So, this g dash x will be 0. So, at our root, so this g dash x star equal to 0. So, this is less than 1. So, it will converge. So, if f dash x equal to 0, so we have to see what is the meaning of f dash x equal to 0. So, f dash x equal to 0. So, the tangent, that is, this is f dash x. So, in this case at this point, for example, at this point, so it is tangent to this equation. So, if we are taking a point, for example, let us take this, and we are taking a point where this it is horizontal. So, if the f dash x is horizontal, that means it will not cut the. So, if it is horizontal, then we cannot proceed the iteration. So, in that case, we have to modify the point x k. So, if our f dash x k equal to 0, then f dash x k is nothing but the tangent to the curve. So, if the tangent to the curve is 0, that means it is horizontal. So, we cannot get the next iteration point. So, for that purpose, we have to take, or we have to modify this x k by x k plus delta, such that this f dash x k plus delta not equal to 0. So, this way we can modify the thing. So, as we know, for nonlinear equation there are multiple solutions. So, we have to take different interval to find the solution. Also sometimes, so one has to use this, or one can write this x k plus 1 equal to x k. So, previously we have derived this x k minus f x k by f dash x k. So, sometimes it is useful to use a operator delta here to which will either accelerate the iteration or to reduce the iteration. So, if this delta less than 0, less than 1. So, if delta less than 1, the iteration is deaccelerated, although the convergence becomes lower. So, this may be desirable if the function f x is not smooth with many local variations. So, in that case, so it will deaccelerate, but if we are taking delta greater than 1, so it will accelerate. So, you just see if delta greater than 1, this term will be small. So, if delta is greater than 1, the iteration is accelerated. So, the iteration, so here it is deaccelerated. iteration is deaccelerated and here the iteration is accelerated. But if the iteration is accelerated, sometimes it will miss some of the roots of the equation and it may miss some of the equation. So, we have to be careful. So, while taking this value of delta, sometimes it may so happen that, so by taking for example, let us take delta equal to 2. So, in that case sometimes it may oscillate also. So, for example, let us take this is the thing. So, this is the curve. So, this is x n. So, we have taken this is x k, then this x k plus 1. So, this is x k plus 1. So, then the next k if we are taking here. So, let the next k we have taken it here. So, you can see if we are taking this delta equal to 2. So, initial point we have taken here, x k we have taken here. The next point we have taken, that is this is 1, this is x k plus 2. So, we have taken the next point here. So, when we are taking the next point here, so you just see our slope is, so this point is taken by drawing a slope here. So, the slope is, so we will get the point by taking a slope here, drawing the slope at this point. This is k plus 1. So, this is the root. So, this is the root, and if our equation we are taking in such way that, so this is x k plus 1, this is x k plus 2, and the here also if we are drawing the tangent and it is passing through the same point. So, let it is passing through the same point. So, in that case you can see, so it will oscillate between these 2 points. So, we have started with this one. So, this is the next point we have taken, this is the next point we got. So, as we are taking delta equal to 2, so it will miss the root, and it will oscillate between these 2 points. So, we have to choose this delta, this accelerated value in such way that, so it should not miss, and we have to get the root properly. And also in case of nonlinear system, so already nonlinear equation as multiple roots are there. So, for example, we can take a function like this. So, this is one root, this is the second root, third root, fourth root. So, we have several roots. So, this is x and this is f x. In some cases there may not be any root, and in some cases, so there will be multiple roots also. For example, if you take f x equal to sin x, so we have several roots are there. Similarly, if we are taking a function, so if we are taking a function, so here the roots does not exist, then it will have 0 root also. So, we can have 0 root or multiple roots in this, and we must be clear how to find. For example, let us take this equation f x equal to x square plus 4. So, in that case, so we have this x square equal to minus 4 or x equal to plus minus 2i. So, here it is imaginary and we do not have a real root. So, as real root is not here, so we do not have a root, and in this case we have a number of roots are there. So, depending on the equations what you are solving, so we must take the initial value much closer to the roots of the equation to have a very good convergence. So, one can study the convergence of this Newton-Raphson method also. So, this is for a single equation. So, if we have a number of equation, so it can be written, this equation can be written using, for example, this f x. So, in case of multivariable or in case of multiple variables are there. So, we can write using this f x can be written as this f1x. So, it will be f1x, f2x and fmx. So, let we have m variable. So, we can write or m equations, m equation with n variables. So, we can write either m or n, m equal to n, number of equations may be equal to number of variables. Sometimes it may be different also. So, m number of equations may be different than number of variables. So, in that case these f functions can be written equal to, for example, this is f1. So, this variable may be x1, x2 and we can write up to xn. Similarly, we can have f2, x1, x2, xn and fm x1, x2, xn. So, we can have n number of variables and m number of equations. So, to find the roots at which this occurs, so it must be equal to 0. So, we can write this is equal to 0, 0, 0. So, similar to previous case, here also we can expand this equation using the Taylor series, where we can write this f m x, we can write or we can expand this thing like this. So, this will be equal to f m x 0 plus summation n equal to 1 to n, m equal to 1 to n, del f m x 0 by del x n into x 0 minus x 0 n plus the remaining term which we can neglect, or we can tell this is R m x minus norm of x minus x 0 of the higher order norms we can put, and we can neglect this thing. So, here m equal to 1 to m. So, here we can put m equal to 1 to m. So, this first equation, for example, f1x. So, we can write that thing f1x equal to f1 x 0 plus n equal to 1 to n del f m, here we have put 1 del f1 x 0 by del. So, we can vary this n from 1 to n. So, that way we can write this equation. So, here m is the number of equations and n is the number of variable, and we are writing this x 0 equal to x 0 1, x 0 2 and x 0 n. So, these are the initial conditions. So, what we have taken for this one x 0. So, we can write this way transpose of this thing. So, now this f x you can write equal to. So, next we can write, we can expand this thing and we can write this equation. For example, this f x can be written equal to f 1 x f m x. So, this will be written equal to f 1 x 0, f 2 x 0 and f m x 0. So, we are expanding this thing near this x 0. So, plus we can have the. So, you just see this is the differentiation, the terms what we have written here. So, this is the differentiation of this part. So, that thing can be written, or we can expand that thing and we can write this is equal to del f 1 x 0 by del x 1, then del f 1 x 0 by del x 2. Similarly, the last term we can put del f 1 x 0 divided by del x n, and the last term we can expand this thing this way and we can write the last term del f m x 0 divided by del x 1, del f m x 0 by del x 2 and del f m x 0 by del x n into, so this into it will be equal to x 1 minus x 0 1 and x n minus x 0 n plus the residue term or the terms which we can neglect, that is R 1 to R n R m terms we can neglect this thing. So, this thing can be conveniently written as f x 0 plus j x 0. So, this matrix can be written as j x 0 matrix. So, j x 0 into x minus x 0 plus residue. So, this way we can write. So, for a multivariable equation also, so we can write this equation in this form. So, you just see this is similar to that what we have studied in case of the single variable equation. So, here we have to, so we can write this f x equal to f x 0 plus j x 0 and we can write down this thing equal to f x 0 plus j into delta x. So, this is f x 0 into j into delta x. So, this way we can, so this equation is similar to that we have studied in case of the single variable case, and now we can find the next iteration or this delta x. Delta x is nothing but x minus x 0 1, that is the next step what we can take, and we can find the next iteration and we can solve the set of equations in this way. So, there are several software available to find this find the solution using this Newton-Raphson method. So, you can take any of the method and you can any of the program and you can solve this equation. So, it required to find the Jacobian matrix. So, to find Jacobian matrix we can use several methods also. So, numerical differentiation you can use to find the Jacobian matrix. So, after finding Jacobian matrix, the next iteration you can find, and that way you can find the response of the system. So, this way you can use this Newton-Raphson method, and also there are several other methods like the second method and the Muller method. So, those methods you can study. Already we have discussed regarding this Runge-Kutta method, Wilson method and numeric method for solving this differential equation. So, you can take several examples and study these differential equation. So, in MATLAB, so you can write in help of MATLAB and you can see. So, there are several methods to solve this differential equation. So, for example, this first order linear ordinary differential equation. So, you can use this D-solve symbolically you can solve this equation. So, let us see first order linear equation dy by dt equal to Ty. So, you can first represent this y as a symbolic variable. To represent the symbolic variable, so you can write SYMS equal to YT. The purpose of showing this thing is that you can use this MATLAB help file to or this demo file. So, there are several things are there, solution, support. So, here documentation, examples, function, video. So, all these things are there. So, in the help file, so you can use this help file to find the commands what you can use for your purpose. So, in this case, this is a first order differential equation dy by dt equal to Ty. Here you can write this symbolic YT, SYMS represent the symbolic. So, if you are going to finds in a symbolic way the solution. So, you have to use this SYMS. So, then you can write, so define this equating using this double. So, this way 2 equal to you can write. So, for example, so you have written ODE equal to DIFF YT equal to T into Y. So, now ODE T you have written equal to DIFF YT comma T. So, equal to T into YT. So, to solve this equation, so you can use this dsolve command. So, you can write y solve T equal to dsolve ODE. So, ODE you have already defined ODE T. So, this is the function you are writing ODE equal to DIFF YT equal to T star Y. So, D function, so differentiate using D function. So, here the function is differentiated using this D function, that is why this ODE equal to DIFF YT equal to T star Y. So, then you can use this dsolve Y solve T equal to dsolve ODE to solve this equation, and you can find it is showing you the solution equal to C1 e to the power T square by 2. So, if you know the solution of your own also, so you can solve it. So, dy by dt equal to Ty. So, you can write dy by y, you can write dy by y equal to dy by y equal to T dy. So, now integrating both the sides, so you have this ln y equal to, so this is equal to your T square by 2. So, that is why you can write this y equal to some using some constant also you can write. So, this will be equal to e to the power this thing C1 e to the power T square by 2. So, here you just see, so you have not given any initial condition, that is why this C1. So, you are getting one constant C1. So, if you provide this initial condition, so then this constant also it will determine and it will find the solution. For example, if the constant is you have given, that is the initial condition you have given, let y 0 equal to 2 you have given. So, you have written this way, condition equal to y 0 equal to 2. So, then y solve T equal to d solve ODE condition. So, you have written, so it will solve, and in that case you will get 2 e to the power T square by 2. So, here at theta at t equal to 0, y value is 0. So, if you substitute that thing in here, so you have y equal to this. So, as at t equal to 0, so y 0 equal to C1. So, this part you just see t equal to 0 e to the power 0 e to the power 0 equal to 1. So, this becomes 1. So, C1. So, y 0 equal to C1 equal to 2 you have given. So, that is why your C1 becomes 2 now. So, that is why you got the solution. So, you got the solution y equal to 2 e to the power T square by 2. Similarly, you can solve many other equation. So, here, so dy by dt plus y square equal to 1. So, if you have a first order differential equation, so you have only single constant. So, if you have second order equation, so you require 2 constant, and if you have third order equation, so you require 3 constant to solve these equations. So, here for example, another examples you just see d square y by dt square equal to cos 2x minus y. Actually, this equation, so you have seen several times, it is d square y by dx square plus y d square y by dx square plus y equal to cos 2x. So, this is similar to a force vibration case you have seen. So, this is mx double dot plus kx equal to f sin omega t. So, that solution already is known to you. So, it will have 2 solutions. So, first part, so you will have, so by putting this is right hand side equal to 0. So, you have the complementary function. So, with solution, so the coefficient of y equal to 1. So, you have a solution. So, the solution y for complementary part it is equal to it is equal to, so you can write C1 cos or sin you can use, C1 cos, here omega equal to 1. So, C1 cos t plus, you can write this way, C1 cos t plus phi the phase. So, this is the complementary part, and then you can have to add the particular integral. So, it will have two part. So, you can know the solution of this equation. Particular integral also you can find by putting this cos 2x by d square plus 1. So, here your d square you have to substitute. So, d square can be substituted by minus 4. So, minus 4 plus 1, this becomes minus 3. So, then this becomes cos 2 minus cos 2 x by 3. So, that will be the, that way you can solve the equation. So, with different initial condition, the C1 and phi can be obtained. So, either you can write this way or you can write the solution this way also, cos t plus C2 sin t plus the particular integral part. So, that way you can write the solution. So, now by using the symbolic software, so this way you can write. So, define the equation and condition. The second initial condition involved. So, here y equal to 0 is the displacement equal to 0, y dash 0, that is the velocity equal to 0. So, you can put SYMS equal to y, SYMS yx, dy equal to diff y. So, it will differentiate. So, OD diff y x2 equal to cos 2x minus y. So, condition 1, that is y 0 equal to 1, condition 2 equal to dy 0 equal to 0. So, to solve this thing, so you can put this condition 1, condition 2, y solve x equal to d solve. So, you are using the command d solve here, d solve ODE condition. So, your y solution equal to, so you can simplify the solution and you got the solution this. So, 1 minus 8 sin x by 2 to the power 4 by 3. So, similarly, for a third order equation you can find. So, previously I told regarding this Runge-Kutta method to solve this equation. So, here some more examples are given in this MATLAB help. So, as you will get this MATLAB in this course to use MATLAB. So, you can conveniently use this MATLAB help file to write down your own equations and solve this equation. Some functions using D solve are written here. Similarly, you can use this ODE. So, there are several ODE functions are there. So, you can use this ODE 2, 3, particularly this is for stiff equations you can use, then ODE 4, 5 you can use. So, ODE 4, 5 or ODE 2, 3 you can use, and if you have a delay differential equation, so there you can use this DDE 2, 3 you can use delay differential equation. So, we will see one delay differential equation and how to solve it using both this DDE and this method of multiple scale next. So, let us see one delay differential equation. So, this is for a flexible tool and workpiece in turning operation. So, this is the work of my PhD student Arnab Chand. So, now he has defended his thesis, now he is Dr. Arnab Chand. So, you can see this equation. So, here in turning operation both the tool and the workpiece have been considered to be. So, this is the tool, you can see this is the tool and this is the workpiece. So, when it is cutting, so there are several undulations. So, previous undulations are present on the surface of the workpiece. So, as the workpiece is flexible, so there is vibration of the workpiece. So, when it is cutting, the tool is cutting, so it may cut the portion. So, where previously, so depending on the previous cut, so sometimes there will be material or sometimes there may not be material, but we are considering always the tool is in contact position with the workpiece. So, the detailed derivation, so you can see the work Arnab Chand. So, you can write down this equation, you can see the equation can be written in this form, that is, for one we are taking x1 and the other one for the tool, for example, let us take this x1 and workpiece x2. So, we can write down this equation of motion in this form, that is x1 double dot plus 2 epsilon omega 1 1 mu 1 x1 dot, this is due to damping, plus omega 1 1 square x1 plus epsilon alpha 1 2 x1 square plus epsilon square alpha 1 3 x1 cube plus epsilon omega 1 1 square beta 1. So, here you just see the term we are using x1d, that is the delay term we are using x1d, x1d and x2d. So, these are the delay term. So, that is, it depends on the previous cut. So, at x t minus, so x1 t minus tau, x1d is nothing but x t minus tau. So, in the present time is t. So, it depends on the past time. So, if you are taking a time delay of tau, so this x1 will depend on the time t minus tau. So, we have to go to the past history to see, so what is the displacement of that point. So, that is x1d. Similarly, we have this x2d. So, this is equal to x1d minus x1 plus x2 into x2d, x2 minus x2d, and then we have a forcing term epsilon f cos omega t. Similarly, for the workpiece we can write x2 double dot plus 2 epsilon omega 2 1 mu 2 x2 dot. So, this part, the left side part of the equations are similar to that you have seen in case of the doping equation, but in the right hand side. So, we have some term, some forcing term and plus the delay equation. So, we are using this delay differential equation as delay terms is used in this equation. So, we have this delay differential equation. So, this delay differential equation actually you can solve by using this ODE also, by using this Runge-Kutta method also, but here you have to consider. So, when you are taking this x1d, you have to consider the time. So, you have to consider the previous value of x1 at time t minus tau. So, here let us use this method of multiple scales and DDE, both the things has been used here. So, if you are taking method of multiple scale, so you can follow the standard procedure of method of multiple scale. The only difference is that, so you have to define. So, for example, x1 is defined as x11 t0 t1 plus epsilon x12 t0 t1 plus epsilon square x13 t0 t1, where already you are acquainted with that Tn is nothing but Tn equal to epsilon n t. So, this is the thing already you know. So, these are different time scales we are using for x1. x1 is the current position and x1d is the delayed position, that is x1d t minus tau. So, can be written in this form. So, this is the new thing you have to check. So, x1d t minus tau can be written as x1d t0 minus tau. So, then this t1 minus epsilon tau. So, that way we are, so this t1 is replaced by t1 minus epsilon tau and t0 is replaced by t0 minus tau. Similarly, the higher order or other time t2, t3, so that way also can be defined. So, it will be just epsilon n into t minus tau. It can be replaced, Tn can be replaced in delay term by epsilon n into t minus tau. So, epsilon to the power n into t equal to your Tn. So, that way, so this epsilon 1d term is defined. Similarly, x2 we can define x21 t0 t, t0 t1, t0 t1 t2. So, that way we can define. So, t1, so this is t1. Similarly, we can define for x2d, and following the similar procedure of method of multiple scale. So, we can separate the terms with order of epsilon 0, epsilon 1, so epsilon 2. So, if you just see we can separate, we can write up to epsilon square, and then we know the solution of these equation x2 square x11 plus, So, this is the epsilon to the power 0. So, for the second equation also we know. So, this is for the first equation and this is for the second equation. So, now we have 6 equations we got and we got their solutions. So, now following the procedure described in case of the method of multiple scale. So, we can get a set of reduced secular terms and by eliminating the secular terms. So, we can get the reduced equations. So, these are the reduced equations we got A 1 dash A gamma 1 dash A 2 dash gamma 2 dash. So, the first order solution can be written in this form. So, after getting the solution, so we have taken this. Okay, for trivial state we can convert that thing to P1 P2 form and taking these physical parameters. So, we have shown that the DD23. So, if we solve this equation using DD23 delay differential equation in MATLAB, we have this command DD23 and this method of multiple scale second order. So, you can see exactly it is matching. So, you can see the time response, it is exactly matching both the DD23 and method of multiple scale responses obtained by method of multiple scales are matching. So, you can verify or you can solve this delay differential equation, any delay differential equation using this method of multiple scale. Also, the advantage of using method of multiple scale is that, so you can plot the frequency response plot and other study also you can do parametric variations also you can do easily by using this reduced equation. So, you learn how to use this ODE ordinary differential equation, solving this ordinary differential equation and also to solve this delay differential equation. So, by using Runge-Kutta method also, so you can get the same response that we have got in this DD23 by replacing this x1d equal to x t minus tau. So, you have to keep the previous history and you have to substitute that history to find the response of the system. So, here for a different value of tau also it is verified. So, the response has been plotted. So, several variations have been carried out. So, this way you can solve the delay differential equation. So, already you have seen this how we have solved this doping equation. So, in case of the doping equation we have used this ODE45. So, here ODE45 of MATLAB have been used to find the response. Here you can see we got the chaotic response of the system and also, so these are the code written. So, previously it has been shown. So, you can get periodic response, quasi periodic response and chaotic response for by taking different value different system parameter. So, you can get these equations or get these response. So, next class we are going to study regarding the Poincare section, FFT and Lyapunov exponent to characterize different type of responses, particularly these chaotic responses. Thank you very much.